Hi, welcome to our Data Science and Cosmology project. Our motivation for this project is to show how data science can be used in cosmology. We are attempting to closely model results obtained through traditional methods in physics, in particular the Hubble Constant, galaxy-type clustering, and a classifier for astro objects, namely quasars versus galaxies. As far as ethical considerations, no personal data was exploited in the making of this project. Shout out to the flat earthers. To acquire the data, we had to get on the Sloan Digital Sky Survey website and to run a SQL query. In order to do that, we had to learn a little SQL in the process. We proceeded to sample randomly and at largest n so that we would be able to make relatively accurate conclusions for the Hubble constant. Next, we had to fix some data types, do some unit conversions, and then calculate some new variables so that we would be able to find flux, velocity, and distance, and then plot velocity versus distance, attaining the slope of the line, which is the Hubble's constant. Moving on to the exploratory data analysis, we decided to run a scatter matrix to try to find any trends between the different variables that we were plotting. We had originally planned to use the red band of the electromagnetic spectrum because of its sensitivity to determine distance. We then proceeded to realize via the scatter matrix that the green band yielded much better results. We also found, due to the exponential calculation of the flux, there was an exponential error in the data. Because of this, we decided to build our regression model using the log of the distance rather than just the distance itself. In our regression model, to determine the Hubble parameter, our experimental measured value was 43.57285 kilometers per second per megaparsec, and a typical r-squared value of each model was around 85%. This means that the variance between the log of the distance and the velocity is explained by our models. In the end, we have found that larger data sets did not lead to better results. Adding more data points did not increase our r-squared value, neither did it yield a more accurate value for the Hubble parameter. Moving on to our clustering and classification models, we do a k-means clustering and a dB-scan clustering in effort of separating different types of galaxies. And here is an actual diagram from Wikipedia of blue versus red galaxies. Our SVM model was able to predict whether an object was a galaxy or a quasar on test data with an average 98.3% accuracy. Overall, we were thrilled with our results. Our value of 43.57 kilometers per second per megaparsec is actually incredibly close to Edwin Hubble's original estimate of 55. Quasar velocities and distances are distributed so erratically that they do not yield accurate results for the Hubble parameter. And despite the erratic behavior, it is possible to use machine learning techniques to separate them from traditional galaxies. Sometimes to obtain better results, it is better to revise your methodology than to obtain more data.